In this video, I give a quick demonstration of multiple trust algorithm and trust strategies based on two different scenarios. First, let's start by opening the first scenario and start provisioning. Basically, this scenario is composed of 7 different services, S1 to S7. And it shows a snapshot of an application in which S1 so far has been called 1,000 times, and S1 has called this to 900 times, and so on. So basically, one of the features of this UI is that it's extremely flexible, and we can save any arbitrary snapshot of the execution of the SO application, and later on we can load and start from there, start executing and experimenting from that point. Let's take a look at the trust tab. As you can see, we have 2 different strategies and 2 different algorithms. We can select any of the strategies and combine that with one of these trust algorithms. Based on these 2 combinations, we can query the trust value, the composite trust value of each of these services. Let's start by querying S1 based on pessimistic strategies and coarse grain algorithm. The pessimistic strategy is based on the principle of the weakest link in information security. It says that in any given system, the security of the whole system is equal to the security of its weakest component. For example, here, if we take a look at this whole application, we will see the lowest trusted service is 0.1 here, S3. So if we query S1 here, we will see that the aggregate trust will be 0.1, which is the trust value of S3. These trust strategies can be very useful for the mission critical or highly sensitive applications like military grade applications. But it can be very restrictive in normal commercial applications. So we may require to come up with new trust strategies. For example, we have defined an averaging strategy. In the averaging strategies, we define the composite service trust as the average trust of all the participating services in the composite trust. For example, here, if we average all the trust values from S1 to S7, the average trust will be 0.47. But one of the main restrictions of this approach is that it doesn't consider how services has interacted previously. For example, S1 has called S2 900 times in the previous history during its lifetime, and S1 has called S7 just once. But the averaging strategy just consider both of them as equal services, and each of these services will have similar weight in the calculation of the aggregate trust. To make this calculation more precise and calculate and consider these weights into account, we defined graph reduction global algorithm. The detail of this algorithm is available in the dissertation. I don't want to cover the details here, but the idea is that for any arbitrary service graph, we try to reduce that graph based on its weights, and by reduction we will come up with the aggregate trust. For example, if the query S1 here, the aggregate trust will be 0.58, which is higher than 0.47 based on the coarse grain global algorithm. The reason here is that in the graph reduction algorithm, we see that the weight of S3 is much lower than weight of S2 and even S1 here, which has a weight of 1,000. Therefore, if we consider all these weights and calculate this composite trust, the trust value will be higher than a trust threshold, and shows that so far S3 can be considered as trusted. based on the whole previous history of execution. We can have other different combinations. For example, the coarse-grained algorithm can be improved by weighted averaging strategies. The idea behind weighted averaging strategies is to give each service a weight. For example, S1 here has a connection to 6 different other services, but each services S2 to S7 have just one incoming connection. To consider weighting, we applied PageRank algorithms, which shows each service that has more input and output connections will have a higher weight. By applying that PageRank algorithm, we can assign new weights and alleviate the problem of the lack of considering these weights by considering this PageRank weight. Now let's see how this works so far. We see that by taking this PageRank weight, this trust algorithm has increased from 0.47 to 0.53. And the main reason, as I said, is that S1 has a much higher weight and is much more important compared to S2 to S7. Because if S1 is untrusted, then none of the inputs from other services will be trusted as well. In overall, the effect of S1 on the whole application is much higher than any of these other services. Therefore, the weight of S1 is higher, and since S1 is more trustworthy, the trust is 0.7, then the overall trust value has increased to 0.53 from 0.47. This is another strategy that we can use. The main difference between graph reduction and coarse-grained is that the coarse-grained is less computationally intensive, but the graph reduction requires more computation, and it could be the cost of running this algorithm in extremely large graphs would be higher. So in some realistic and large scale scenarios, the service providers may decide to use coarse-grained with weighted averaging instead of graph reduction. But the graph reduction has the perfect precision in calculating the composite trust. So it's a trade-off here that we need to take it into account. And as you can see, we have two different composite trusts here. We have aggregate trust and session trust. Aggregate trust says the trust value of the whole composite service composition from the beginning of the execution of the SOA application, which considers all these weights and everything. But the session trust is the trust value of the latest invocation. For example, if we call this SOA application, we will see that it shows all the services have been accessed, and if we update the trust, we see that each of these weights increase by 1, which shows that we have called S1, S2, and S7, all of these trust values. Then let's try by querying the session trust for S1 here. As you can see, the session trust is 0.47. Again, this is the average of all these services. If we calculate the average for the graph reduction algorithm, this is again 0.47. This is very interesting because in the session trust, we don't care about the previous history. We just want to know what's been the trust value of the latest invocation, which considers all these weights as 1. For the session trust, we see that the aggregate trust, the session trust is the same for both graph reduction and coarse-grained global algorithm. But if we query the aggregate trust, we see the trust is different, which includes all these weights and the previous history. The session trust is used for the is used for the session report, which will be given to the user, which says, for example, here, no data leakage has happened, no policy has been violated, and the session trust is 0.47, and the composite trust is 0.58. As I previously mentioned, using this UI we can create arbitrary complex scenarios. For example, here I show a more complex scenario, and I already have provisioned the scenario in the service. So if we query this S0 here, we see that the trust value is 0.5. Even having this much larger weight compared to S5 and having S1 have trust 0, still it shows that the overall trust, aggregate trust is more than threshold, and overall it's considered as a trusted composition. But using the graph reduction algorithm, we see that it considers all these weights and shows that the trust value is less than the threshold, and this composition is untrusted. Further, we can, for example, if we change these values again to 0.5, and we change this service now, reduce the trust value of this service to 0.15. Now we can query S0 with pessimistic, and we can see that it shows the trust value of the lowest trusted component or service here, which is 0.15, even though it's 3 hop away from the service that we are querying. This is this was a very quick overview of this trust algorithm, and the details, implementation details, and the algorithmic aspects of that are available in the thesis.